Before we dive into this extraordinary story, if you appreciate detailed historical accounts that reveal the technological realities of World War II aviation, please subscribe to our channel and hit the notification bell so you never miss our comprehensive documentaries. In the vast Pacific theater during 1943, Japanese Zero fighters had dominated aerial combat for 2 years through superior maneuverability and experienced pilots who had honed their skills in the China campaigns. Japanese fighter doctrine emphasized agility and dogfighting prowess, accepting minimal armor and armament to achieve the lowest possible weight and the tightest turning radius. But when American F-4U Corsair fighters began appearing over the Solomon Islands in early 1943, Japanese pilots reported encounters with an opponent that seemed to operate by entirely different rules. An aircraft that refused to engage in turning fights and instead used overwhelming speed and climb performance to dictate combat on its own terms. When a damaged Corsair made an emergency landing on Japanese-held Bougainville in September 1943 and was captured nearly intact, Japanese engineers finally received the opportunity to understand the weapon that was systematically destroying their best pilots. What they discovered during intensive evaluation shattered every assumption about fighter design and revealed that the Corsair's Pratt & Whitney R2800 engine, producing over 2,000 horsepower, could outclimb the Zero by 3,000 feet per minute, a performance disparity so vast that no amount of pilot skill or tactical brilliance could overcome it. This is the story of how Japanese engineers flew and dissected a captured Corsair, how each test revealed another crushing advantage, and how they came to understand that Japan's lightweight fighter philosophy had become a death sentence for pilots facing an opponent with overwhelming power and technological sophistication. Before we dive into this extraordinary story, if you appreciate detailed historical accounts that reveal the technological realities of World War II aviation, please subscribe to our channel and hit the notification bell so you never miss our comprehensive documentaries. The morning of September 28, 1943 broke humid and oppressive over the Yokosuka Naval Air Technical Arsenal outside Tokyo when Captain Minoru Genda received the urgent communication that would fundamentally alter his understanding of aerial warfare. An American VOT-4U-1 Corsair fighter, damaged during combat over Bougainville in the Solomon Islands, had made a forced landing on a Japanese-held airstrip and had been captured with its pilot before significant destruction could occur. The aircraft was being carefully disassembled and would be transported to Japan for detailed evaluation. Genda, a brilliant tactical thinker who had helped plan the Pearl Harbor attack and who now served as a senior advisor on fighter development, understood immediately that this capture represented an intelligence opportunity of incalculable value. For months, disturbing reports had been flowing in from frontline fighter units describing encounters with a new American fighter that seemed almost invulnerable to traditional Japanese tactics, the Mitsubishi A6M. Zero had been the undisputed master of Pacific skies since its combat debut over China in 1940. The Zero's design philosophy reflected Japanese naval aviation doctrine that emphasized range, maneuverability, and climbing ability while accepting minimal protection and firepower to achieve the lowest possible weight. The A6M2 Model 21, the most common variant in service during 1941 and 1942, weighed approximately 5,300 pounds empty and was powered by a Nakajima Sake 12 engine producing 940 horsepower. This gave the Zero an exceptional power-to-weight ratio and performance characteristics that made it extraordinarily agile. The aircraft could turn inside any Allied fighter, could climb rapidly to intercept altitude, and had the range to escort bombers on extended missions. In the hands of experienced Japanese pilots who had trained for years and who had combat experience from China, the Zero had been devastating against Allied opposition in the first year of the Pacific War. American, British, and Dutch pilots flying obsolete fighters like the Brewster Buffalo or P-40 Warhawk found themselves hopelessly outmatched by Zeros that could outturn, outclimb, and outrange them. But the Zero's dominance had been built on a foundation that was beginning to crumble by 1943. The experienced pilots who had made the Zero so deadly were being killed in combat faster than they could be replaced, and the replacement pilots receiving abbreviated training could not match the skill levels of their predecessors. More critically, American fighters were evolving rapidly based on combat experience and were being produced in quantities that Japan could never match. The Grumman F-6F Hellcat had appeared in mid-1943 and was proving to be a formidable opponent, faster and more rugged than the Zero while still reasonably maneuverable. But the reports about the VOT F-4U Corsair were even more alarming. Pilots who encountered Corsairs described an aircraft that was faster than anything Japanese, that could climb at rates that seemed impossible, that could dive away from any engagement a Zero pilot tried to force, and that could absorb battle damage that would destroy a Zero while continuing to fight effectively. The Corsair seemed to represent a fundamentally different approach to fighter design, one that prioritized raw power and structural strength over the lightweight agility that Japanese doctrine had always emphasized. The captured Corsair arrived at Yokosuka on October 15, 1943, transported in pieces by submarine and fast transport from Rabaul. The fighter had been carefully disassembled by Japanese ground crews who had some experience with captured Allied aircraft, and the damage from combat and the forced landing was relatively minor. American attempts to destroy the aircraft with demolition charges had been interrupted by Japanese troops, and the pilot had been captured before he could complete the destruction. The Corsair represented the most advanced American fighter yet captured intact, and every naval aviation officer and engineer at Yokosuka understood that examining this aircraft could provide insights that might help stem the growing tide of Japanese losses in air combat. Captain Genda assembled an evaluation team that included Lieutenant Commander Saburo Sakai, one of Japan's leading fighter aces with over 60 confirmed victories, Commander Jiro Horikoshi, the brilliant engineer who had designed the Zero, and a team of technical specialists from Nakajima and Mitsubishi who would examine every aspect of the Corsair's design and construction. When Horikoshi first saw the reassembled F4U-1 Corsair in Yokosuka's main hangar, his immediate reaction was one of awe mixed with apprehension. The Corsair was enormous compared to Japanese fighters, with a distinctive inverted gull-wing design that gave it an aggressive, purposeful appearance. The aircraft weighed approximately 8,900 pounds empty, nearly 60% heavier than the Zero. The propeller was massive, a 13-foot diameter Hamilton Standard unit that dwarfed the propellers on Japanese fighters. The entire aircraft projected an impression of power and ruggedness that was fundamentally different from the refined delicacy that characterized the Zero. Horikoshi walked slowly around the Corsair, noting the heavy construction, the thick wing, the substantial landing gear, and the overall impression of an aircraft designed to withstand tremendous stresses. This was not a lightweight dogfighter built to the limits of structural efficiency. This was a robust weapon platform designed to deliver overwhelming firepower while protecting its pilot and absorbing battle damage. The evaluation began with a detailed examination of the Corsair's Pratt & Whitney R2800 double Wasp engine, and what the Japanese engineers discovered immediately explained much of the aircraft's performance. The R2800 was an 18-cylinder Turreau radial engine with a displacement of 2,804 cubic inches, making it one of the largest and most powerful piston engines in operational service anywhere in the world. The engine produced 2,000 horsepower for takeoff and maintained substantial power at altitude. Through a sophisticated two-stage, two-speed supercharger system, Commander Yamamoto Kiyoshi, Yokosuka's chief propulsion specialist, led the engine examination with a team of engineers who had extensive experience with Japanese aircraft engines. What they found was both impressive and deeply disturbing from a Japanese perspective. The R2800 represented a level of engineering sophistication and manufacturing precision that Japanese industry could not match. The engine's construction revealed manufacturing capabilities that exceeded anything available in Japan. The cylinder barrels were machined to tolerances measured in thousandths of an inch, with surface finishes that reduced friction and improved cooling efficiency. The pistons were forged aluminum alloys using metallurgical processes that produced components with exceptional strength to-weight ratios. The crankshaft was a massive forging that had been heat-treated and precision machined, capable of transmitting 2,000 horsepower reliably without the cracking or failure that plagued Japanese engines operating at much lower power levels. The supercharger system was a masterpiece of mechanical engineering, using precisely machined impellers and sophisticated intercooling to compress intake air efficiently while managing the heat generated by compression. Every component showed evidence of precision manufacturing, rigorous quality control, and engineering sophistication that reflected years of development and massive industrial investment. Yamamoto compared the R2800 to the Nakajima Sakai engine that powered the Zero, and the disparity was staggering. The Sakai produced 940 horsepower from 14 cylinders, less than half the R2800's output. The Sakai weighed approximately 1,200 pounds, while the R2800 weighed about 2,350 pounds. But the power-to-weight ratio still heavily favored the American engine. More significantly, the R2800 was designed for sustained operation at high power settings with cooling systems, lubrication systems, and structural components that could handle continuous maximum power without overheating or mechanical failure. The Sakai, by contrast, was designed for moderate power settings with occasional bursts of maximum power for combat maneuvering. Sustained high-power operation led to overheating, excessive oil consumption, and increased risk of mechanical failure. The R2800 could produce its rated power hour after hour, day after day, with remarkable reliability. The Sake required careful power management and frequent maintenance to remain operational. The supercharger technology particularly impressed and depressed the Japanese engineers. The ART 2800's two-stage, two-speed supercharger maintained engine power at altitudes where Japanese engines were gasping for air. The first stage compressed intake air to intermediate pressure. The intercooler reduced the temperature of that compressed air to increase its density. Then the second stage compressed it further before delivery to the cylinders. This sophisticated system allowed the R2800 to maintain high power output at altitudes exceeding 25,000 feet, where the Sake's single-stage supercharger struggled to provide adequate boost pressure. Japanese engineers had understood the principles of two-stage supercharging for years, but implementing such systems required manufacturing precision, materials quality, and engineering resources that Japan could not spare for fighter engine development. The result was that Japanese fighters lost power rapidly above 20,000 feet, while American fighters equipped with turbocharged or two-stage supercharged engines maintained high performance at altitudes where Japanese pilots found their aircraft sluggish and underpowered. Lieutenant Commander Sakai, the experienced fighter pilot, focused his attention on the Corsair's structure and design philosophy, and what he found represented a fundamental challenge to everything Japanese fighter doctrine had taught him. The Corsair's airframe was massively strong, built to withstand stresses that would tear apart a Zero. The wings were thick and robust, designed to handle the tremendous forces generated during high-speed dives and violent maneuvering. The fuselage was constructed of heavy aluminum alloys with internal structure that provided redundant load paths, so that damage to one structural member would not lead to catastrophic failure. The landing gear was extraordinarily robust, designed to withstand carrier landings with vertical sink rates that would collapse the Zero's delicate landing gear. The entire aircraft was built with structural safety factors that seemed almost wasteful from a Japanese perspective, where every pound of excess weight was viewed as a performance penalty that must be avoided. But Sakai began to understand that what appeared as excessive weight from a Japanese design perspective was actually a sophisticated approach to survivability and combat effectiveness. And the Corsair's heavy structure allowed it to dive at speeds exceeding 450 miles per hour without risk of structural failure or control surface flutter. The Zero's lighter structure limited its dive speed to approximately 350 miles per hour, beyond which control surfaces became dangerously ineffective and structural failure became likely. This speed differential meant that Corsair pilots could always escape from combat by diving away, while Zero pilots could not pursue without risking their aircraft. The Corsair's robust structure also allowed it to pull high-G maneuvers at high speeds without structural failure, while the Zero's structure limited aggressive maneuvering at high speeds. The weight penalty of robust construction was real, but it was more than offset by the tactical advantages it provided. The Corsair's armament represented another revelation about American fighter design philosophy. The F4U-1 carried 6.50 caliber Browning M2 machine guns, 3 in each wing, with approximately 400 rounds per gun. This armament weighed approximately 1,600 pounds, including guns and ammunition, more than the entire empty weight difference between a Zero and a Corsair. Japanese fighters typically carried two 20mm cannon and two 7mm machine guns, with total armament weight less than half the Corsair's, but the 6.50 caliber guns provided devastating firepower that could destroy enemy aircraft with brief bursts. The high rate of fire, heavy projectiles, and large ammunition capacity meant that Corsair pilots could engage multiple targets or could continue fighting after expending ammunition that would have left Japanese pilots defenseless. The .50 caliber rounds could penetrate armor that would stop Japanese 7mm rounds, and they could cause catastrophic damage to aircraft structures with just a few hits. The evaluation team arranged to conduct engine run tests to confirm the R2800's power output and to understand its operational characteristics. On October 28, 1943, the Corsair's engine was started for the first time under Japanese operation. The sound was unlike anything the Japanese engineers had heard from a fighter aircraft. The massive engine roared to life with a deep, powerful thunder that vibrated through the airframe and shook the hangar. At idle, the engine ran with remarkable smoothness, demonstrating the precision of its internal components and the sophistication of its balancing. Yamamoto advanced the throttle to take off power, and the engine's roar became almost overwhelming. The propeller pulled tremendous volumes of air, creating a hurricane-force blast behind the aircraft that required ground crews to stand well back. The manifold pressure gauge indicated boost pressure that would have destroyed the Sake engine instantly. Yet the R2800 ran smoothly without signs of stress or overheating. The engine held maximum power for 15 minutes without any deterioration in performance or indication of problems. Yamamoto and his team carefully monitored all engine parameters during the run. recording temperatures, pressures, and power output. The data confirmed that the R2800 was indeed producing over 2,000 horsepower, a figure that seemed almost magical to Japanese engineers accustomed to engines producing less than half that power. The specific fuel consumption was reasonable despite the enormous power output, indicating efficient combustion and good thermodynamic design. The cooling system maintained appropriate temperatures throughout the power range, suggesting sophisticated design that balanced cooling effectiveness against aerodynamic drag. Most impressively, the engine showed no signs of the roughness, vibration, or power fluctuation that characterized Japanese engines operating at their limits. The R2800 was running well within its capabilities, with reserve capacity for even higher power output if required. This engine was not being stressed to achieve its rated power. It was operating comfortably in its design envelope with reliability that Japanese engines rarely achieved. The next phase of evaluation involved preparing the Corsair for flight testing, and this process revealed additional insights into American manufacturing quality and maintenance philosophy. The aircraft had sustained some battle damage and damage from the forced landing, but repairs were relatively straightforward because the robust structure meant that damaged components could be replaced, rather than requiring extensive structural repairs. Japanese engineers noted that the Corsair was designed for maintainability with access panels positioned for easy inspection and service, with components designed to be quickly removed and replaced, and with overall design that recognized that aircraft spent significant time undergoing maintenance and that efficient maintenance was as important as good flight performance. Japanese fighters designed primarily for performance and weight minimization were often difficult to maintain with access panels that were too small or poorly positioned, with components that required extensive disassembly to reach, and with overall designs that seemed to assume maintenance was a secondary consideration. By mid-November 1943, the Corsair had been repaired and was ready for flight testing. Captain Genda selected Lieutenant Commander Sakai to conduct the initial evaluation flight, recognizing that an experienced combat pilot would best understand the tactical implications of the aircraft's characteristics. Sakai had flown various captured Allied aircraft during his career and was known for his ability to assess aircraft objectively and to understand how design features translated into combat advantages. On November 18, 1943, Sakai climbed into the Corsair's cockpit for the first time as a pilot. The cockpit was spacious by Japanese standards, with excellent visibility forward and adequate visibility to the sides, though rearward visibility was limited by the large fuselage and raised cockpit position. The instrument panel was comprehensive and logically arranged, with all critical instruments easily visible and all controls within comfortable reach. Sakai noted that the cockpit reflected understanding of pilot needs developed through operational experience, with features like the excellent gun sight, the comfortable seat, and the logical systems layout all contributing to pilot effectiveness. Sakai started the R2800 engine and felt the tremendous power transmitted through the airframe as the engine settled into its characteristic rumble. He conducted pre-flight checks, familiarizing himself with the controls and systems, then taxied the Corsair to the runway. Japanese observers lined the field, eager to see the American fighter perform. Sakai advanced the throttle for takeoff, and the Corsair's acceleration was breathtaking. The massive propeller bit into the air with tremendous authority, and the aircraft surged forward with power that far exceeded anything Sakai had experienced in Japanese fighters. The Corsair lifted off after a remarkably short ground roll despite its substantial weight, and Sakai retracted the landing gear and began climbing away from the field. What happened next shocked every observer who witnessed it and would fundamentally alter Japanese understanding of what American fighters could do. Sakai established a climb at the aircraft's optimal climb speed and watched in amazement as the altimeter wound upward at a rate that seemed impossible. The Corsair was climbing at over 3,000 feet per minute, ascending like an elevator rather than an aircraft. Sakai had thousands of hours in the Zero and knew its performance intimately. The A6M20 could climb at approximately 2,800 to 3,000 feet per minute under ideal conditions with a light fuel load, and its climb rate decreased rapidly at higher altitudes as the Sakai engine lost power. The Corsair was maintaining over 3,000 feet per minute climb rate and showing no signs of weakening as altitude increased. At 10,000 feet, the Corsair was still climbing at 3,000 feet per minute, while a Zero would have decreased to perhaps 2,400 feet per minute. At 15,000 feet, the Corsair maintained nearly 3,000 feet per minute, while the Zero would have decreased to approximately 2,000 feet per minute. At 20,000 feet, where the Zero's climb rate would have fallen to perhaps 1,500 feet per minute, the Corsair was still climbing at over 2,500 feet per minute. The implications were immediately obvious to Sakai and to every experienced pilot watching from the ground. The Corsair's climb performance meant that it could control the altitude dimension of combat absolutely. A Corsair pilot could climb above a formation of Zeros and hold altitude advantage regardless of what the Japanese pilots did. If Zeros tried to climb to engage, the Corsairs could climb faster and maintain their advantage. If Zeros stayed low, Corsairs could dive down with tremendous speed advantage, make one pass, and zoom back to altitude using their superior power, climbing away faster than Zeros could follow. The traditional Japanese tactic of using superior climb rate to gain altitude advantage was completely negated. The Corsair outclimbed the Zero at every altitude, and the difference was so substantial that no amount of pilot skill or tactical innovation could overcome it. Japanese pilots would be forced to fight from disadvantaged positions, always below their opponents, always vulnerable to diving attacks, never able to climb away to safety. Sakai continued his evaluation, testing the Corsair's handling characteristics throughout its flight envelope. At high speed, the aircraft was stable and controllable with no tendency toward instability or control difficulties. The controls were heavy compared to the Zero's feather-light control forces, requiring significant physical effort to maneuver aggressively, but they were effective and precise. The aircraft could execute high-speed dives that would have been suicidal in a Zero, pulling out smoothly without excessive G-forces or structural stress. The roll rate was excellent for such a large fighter, allowing rapid changes of direction that would be important in combat. The only area where the Zero retained any advantage was in slow-speed turning ability. At low speeds, the lightweight Zero could outturn the heavier Corsair in sustained turns. But Sakai immediately recognized that this advantage was meaningless in practical combat terms because a Corsair pilot would never allow himself to be drawn into a slow-speed turning fight where the Zero's only advantage could be exploited. After an hour of flight testing, Sakai returned to Yokosuka and landed the Corsair. His debriefing was somber and direct. He stated that the F4U Corsair represented a fighter design philosophy that made the Zero's advantages irrelevant while exploiting Japanese fighters' weaknesses ruthlessly. The Corsair's overwhelming power allowed it to dictate combat terms absolutely, choosing when to engage and when to disengage based purely on the pilot's assessment of tactical advantage. Zero pilots would be forced to accept combat on Corsair terms or to refuse combat entirely, and neither option was acceptable for fighters tasked with defending Japanese positions or escorting bombers. Sakai noted that the Corsair pilot had no reason to ever dogfight with a Zero. He could make high-speed slashing attacks from above, using his speed and climb advantages to engage at will and escape at will, firing his devastating 6-gun armament in brief bursts that could destroy Japanese fighters, then climbing back to altitude faster than Japanese fighters could pursue. The evaluation team conducted comparative testing between the captured Corsair and a Zero to quantify the performance differences precisely. On November 25, 1943, Sakai flew the Corsair while another experienced test pilot, Lieutenant Takeo Tanamizu, flew a Zero. The two aircraft started at the same altitude and began a timed climb to 20,000 feet. The results were devastating for Japanese observers. The Corsair reached 20,000 feet in approximately 6 minutes, while the Zero required nearly 9 minutes. A difference of 3 minutes that represented the time required for the Corsair to climb an additional 9,000 to 10,000 feet. At every altitude checkpoint, the Corsair was ahead of the Zero by increasing margins. The power advantage of the R2800 engine combined with the Corsair's efficient design to produce climb performance that the Zero simply could not match. Additional tests compared maximum speed at various altitudes, acceleration, dive performance, and combat maneuvering. The Corsair was faster than the Zero by 80 to 100 miles per hour at all altitudes, with the speed advantage increasing at higher altitudes where the RT2800 supercharger maintained power that the Sake could not match. The Corsair could accelerate away from the Zero in level flight or in dives, providing an escape option that was always available. In high-speed dives, the Corsair could reach speeds over 450 miles per hour while the Zero's structural limitations restricted it to approximately 350 miles per hour. A 100-mile-per-hour difference that meant pursuing Corsairs in dives was impossible for Zero pilots. The only regime where the Zero held any advantage was in sustained turning at low to moderate speeds, where its light wing loading and low weight allowed tighter turn radius than the Corsair. But as the tests demonstrated repeatedly, exploiting this advantage required the Corsair pilot to make the mistake of engaging in a slow-speed turning fight, something a competent pilot would never do. Commander Horikoshi, who had designed the Zero with such care and who had been justifiably proud of its performance, watched the comparative tests with growing despair. His aircraft had been designed according to the best engineering principles available in the late 1930s. Optimized for the requirements Japanese naval aviation had specified. Those requirements emphasized long-ranged, excellent maneuverability, and adequate climb and speed performance while minimizing weight to achieve maximum efficiency. The Zero had met and exceeded those requirements, becoming the finest carrier-based fighter in the world when it entered service in 1940. But the Corsair represented a fundamental evolution in fighter design based on different priorities and enabled by industrial capabilities that Japan did not possess. The Americans had prioritized power, speed, climb performance, firepower, and ruggedness over the lightweight efficiency the Japanese design emphasized. They had accepted a heavier aircraft with higher fuel consumption because they had the industrial capacity to produce powerful engines and the logistical capacity to supply the fuel those engines consumed. Horikoshi compiled a detailed technical report analyzing the Corsair's design and comparing it systematically to the Zero. His report acknowledged that the Corsair represented superior engineering in almost every measurable category, and that the performance advantages it demonstrated were the natural result of having over twice the engine power combined with robust structure and sophisticated systems. The report calculated that to match the Corsair's performance, a Japanese fighter would need an engine producing at least 1,800 horsepower with a two-stage supercharger, would need to incorporate robust structure capable of high-speed operations, and would need to accept a significant weight increase over existing Japanese fighters. The report noted that Japan lacked engines in this power class, lacked the industrial capacity to produce them in quantity even if they were developed, lacked the high-octane fuel they would require, and lacked the manufacturing precision to build airframes that could exploit their power effectively. The report made specific recommendations for Japanese fighter development, though Horikoshi acknowledged that most could not be implemented quickly enough to affect the war's outcome. He recommended immediate development of more powerful engines, suggesting that Japan's fighter engine program should prioritize power output over fuel efficiency or ease of manufacturing. He recommended structural strengthening of existing fighters to allow higher dive speeds, even though this would increase weight and reduce maneuverability. He recommended increasing armament on Japanese fighters to provide firepower comparable to American aircraft, again accepting weight penalties. Most fundamentally, he recommended reconsidering the entire philosophical approach to fighter design, shifting from emphasis on lightweight efficiency toward designs that incorporated protection, power, and firepower, even at the cost of maneuverability. The report concluded pessimistically that Japan's industrial situation made implementing these recommendations extremely difficult, and that the growing technological gap between Japanese and American fighters would likely continue widening as American industry outproduced and outdeveloped Japan's struggling aircraft manufacturers. The captured Corsair remained at Yokosuka for several more months, used for additional testing and as a training aid for Japanese pilots preparing to face American fighters in combat. Pilots scheduled for deployment to frontline units were brought to Yokosuka to see the Corsair, to hear briefings about its capabilities, and to understand what they would face. The psychological impact of these sessions was significant and generally negative for morale. Pilots who had been confident in their skills and their aircraft returned to their units sobered by the realization that they would be fighting an opponent with overwhelming performance advantages. Some became fatalistic, understanding that survival would depend more on luck than skill when facing Corsairs. Others focused intensely on the tactical approaches that might allow them to occasionally gain advantage, particularly surprise attacks where the Corsair's performance superiority would be temporarily negated. The tactical guidance developed from the Corsair evaluation emphasized avoiding combat whenever possible and engaging only under the most favorable circumstances. Zero pilots were advised never to chase diving Corsairs as they could not catch them, and attempting to do so would leave Japanese fighters vulnerable to attacks from other Corsairs covering their comrades. Pilots were advised to attack only when holding significant altitude advantage, and only when they could achieve surprise, making one pass and then escaping before Corsairs could respond. If engaged by Corsairs from above, Zero pilots were advised to attempt defensive maneuvering toward friendly airfields or areas where other Japanese fighters might provide support, as outrunning or outclimbing the attackers was impossible. The tactical guidance essentially acknowledged that Japanese fighters were inferior and that survival depended on avoiding situations where American performance advantages could be brought to bear. Japanese aircraft manufacturers attempted to develop improved fighters based on lessons from the Corsair evaluation, but these programs were hampered by the same industrial limitations that Horikoshi had identified. Mitsubishi developed the A6M50 with strengthened structure, better dive performance, and modified armament, but the basic design remained limited by the low-powered Sake engine. Attempts to develop more powerful engines consistently fell short due to manufacturing difficulties, material shortages, and the lack of high-octane fuel required for high-compression engines. The Nakajima J2M Raiden and Kawanishi N1K Shidan were designed as more powerful interceptors with engines approaching 2,000 horsepower, but both programs suffered from developmental difficulties and entered service in small numbers too late to significantly affect the war's outcome. Japanese fighters of 1944 and 1945 were generally improved over earlier models, but they never closed the performance gap that the Corsair evaluation had quantified so precisely. The combat record in the Pacific from late 1943 through war's end validated the Corsair evaluation's findings with brutal clarity. F4U Corsair units achieved kill ratios exceeding 10-1 against Japanese fighters, with some squadrons claiming ratios exceeding 20-1. These statistics reflected not just the Corsair's performance advantages but also the declining quality of Japanese pilots, as experienced aviators were killed faster than adequately trained replacements could be produced. But even when flown by experienced Japanese pilots against relatively inexperienced American pilots, the fundamental performance disparity meant that Corsairs typically prevailed. The Corsair's overwhelming power advantage translated directly into combat success that Japanese tactics and skill could rarely overcome. Japanese pilots who survived encounters with Corsairs and who were later interviewed about their experiences consistently emphasized the hopelessness of combat against an aircraft with such superior performance. Several pilots described the frustration of watching Corsairs climb away effortlessly after making attack passes, ascending at rates the Japanese pilots could not match, positioning themselves for follow-up attacks from altitude advantages the Japanese fighters could never contest. One pilot described feeling like he was fighting while wearing weights, every maneuver sluggish and ineffective compared to the power and speed the Corsairs demonstrated. Another described the psychological impact of knowing that the enemy could always escape if threatened, while Japanese pilots in trouble had no escape option available. The Corsairs' performance advantages created a psychological asymmetry that affected combat outcomes beyond the pure physical performance differences. The 3,000 feet per minute climb rate advantage that had so shocked Japanese engineers at Yokosuka became symbolic of the broader technological and industrial gap between Japan and the United States. That single statistic represented the difference between an aircraft powered by a 940 horsepower engine and an aircraft powered by a 2,000 horsepower engine. But it also represented the difference between nations with vastly different industrial capabilities. The United States could design, develop, and mass-produce engines of extraordinary power and sophistication because it had the metallurgical industry to produce high-quality materials, the machine tool industry to manufacture precision components, the chemical industry to produce high-octane fuel, and the skilled workforce to assemble everything correctly. Japan lacked all of these elements to varying degrees, and the cumulative effect was that Japanese aircraft engines consistently lagged behind American engines in power output, reliability, and high-altitude performance. The captured Corsair evaluation also revealed how American aviation had benefited from systematic learning and continuous improvement, based on combat experience. The F4U Corsair was not a revolutionary design that introduced unprecedented technologies. It was an evolutionary design that integrated proven technologies executed with exceptional engineering skill and manufacturing precision. The R2800 engine was an evolution of earlier Pratt & Whitney radials, incorporating lessons learned from years of development and testing. The airframe design used conventional materials and construction methods, simply executed with greater structural margins and better attention to survivability than Japanese designs incorporated. The systems and equipment were sophisticated but not magical, representing steady development by companies that had resources for extensive testing and refinement. The Corsair's excellence stemmed from systematic execution of sound engineering principles backed by industrial capacity that could produce complex components reliably. Japanese aviation had not benefited from similar systematic development processes. Japanese aircraft designs often represented ambitious attempts to achieve maximum performance with minimum resources, accepting technical risks and minimizing safety margins to achieve weight targets. Development programs were chronically under-resourced, with limited prototype construction and inadequate testing. Production aircraft often differed from prototypes due to material substitutions or manufacturing limitations, and these changes were rarely tested thoroughly before implementation. The result was aircraft that sometimes achieved exceptional performance but that lacked the robust reliability and survivability characteristics that prolonged combat operations required. The contrast between Japanese and American development approaches was evident in every aspect of the captured Corsair's design, from the precision-manufactured engine components to the carefully designed cockpit layout to the robust landing gear. Captain Genda, who had initiated the Corsair evaluation program, provided his assessment of its implications in a report to the Naval General Staff in January 1944. His report was characteristically direct and unsparing in its analysis. Genda stated that the Corsair represented a class of fighter that Japan could not match with existing or near-term aircraft. and that the performance advantages it demonstrated would allow American pilots of average skill to defeat Japanese pilots of superior skill in most combat situations. He noted that the 3,000-foot-per-minute climb advantage meant that Corsairs could always hold altitude advantage, which was the most important tactical advantage in fighter combat. He calculated that in formations where both sides started at equal altitude, Corsairs could climb to attacking positions above Japanese fighters in approximately 3 minutes, while Japanese fighters would require 6 to 9 minutes to reach comparable positions if the Corsairs remained level. This differential meant that Corsairs could dominate any engagement, choosing when to attack and when to disengage based solely on tactical advantage rather than being forced to accept combat on enemy terms. Genda recommended significant changes to Japanese fighter tactics and deployment, emphasizing defensive operations where Japanese fighters would operate over friendly territory and could use ground-based radar warning to achieve initial altitude advantage before American fighters arrived. He recommended concentrating fighters for numerical superiority rather than dispersing them to provide widespread coverage, recognizing that individual Japanese fighters or small formations had no realistic chance against competent Corsair pilots. He recommended emphasizing surprise and coordinated attacks that might overwhelm Corsair formations briefly before they could use their performance advantages to escape or counterattack. Most pessimistically, he recommended that Japan accelerate development of unconventional weapons including rockets, bombs, and ramming tactics for use against American bombers, implicitly acknowledging that Japanese fighters could no longer reliably shoot down American aircraft using conventional combat methods. The story of the captured Corsair evaluation became well known within Japanese naval aviation circles, though its findings were not widely publicized to avoid harming morale. The image of a Corsair climbing at 3,000 feet per minute while the Zero struggled to match even half that rate became symbolic of Japan's broader struggles. Pilots and engineers who knew about the evaluation understood that it represented definitive proof of American technological superiority in fighter aviation, and that this superiority was not a temporary condition that could be overcome through determination or tactical innovation. The performance gap was rooted in industrial capacity and engineering sophistication that Japan could not match during wartime conditions with resources already stretched to the breaking point. The captured Corsair met its end in early 1945 when American bombers struck Yokosuka Naval Arsenal during the strategic bombing campaign against the Japanese home islands. The fighter was destroyed in a hangar fire caused by incendiary bombs, bringing to an end its service as both an American combat aircraft and a Japanese evaluation subject. By that time, the lessons from its evaluation had been thoroughly absorbed by Japanese aviation circles, though that knowledge provided little comfort as American air superiority over Japan became absolute and Japanese aviation was reduced to desperate kamikaze tactics born of technological and numerical inferiority. Commander Horikoshi, the Zero designer who had examined the Corsair so thoroughly, survived the war and later wrote extensively about his experiences. He acknowledged in post-war writings that the Corsair evaluation had been one of the most depressing experiences of his career because it revealed so clearly how far Japanese fighter design had fallen behind American developments. He noted that the Zero had been a world-class fighter when introduced in 1940, superior to any opposing fighter at that time, but American fighters had evolved rapidly through continuous development, generous funding, and industrial capacity that could implement improvements quickly. Japanese fighters had remained relatively static due to resource constraints, development difficulties, and doctrinal conservatism. By 1943, the gap had become so large that Japanese fighters were fighting at decisive disadvantages against opponents like the Corsair. Horikoshi expressed regret that Japanese aviation had not recognized earlier the importance of power and protection, and had continued too long with the lightweight fighter philosophy that had served well in China, but that became a liability against modern opponents with superior equipment. Lieutenant Commander Sakai, the ace pilot who had conducted the Corsair's first flight evaluation, also survived the war despite being seriously wounded in combat. He later spoke about flying the Corsair as a revelation that changed his understanding of what fighters could be. He stated that the Corsair's power was unlike anything he had experienced in Japanese fighters, that the feeling of climbing at 3,000 feet per minute was almost intoxicating, and that understanding what American pilots had available made him realize how disadvantaged Japanese pilots had been. Sakai noted that he had always known American fighters were faster and more powerful, but flying the Corsair made the magnitude of the disadvantage visceral and undeniable. He expressed admiration for American engineering that could produce such a capable aircraft, and could manufacture thousands of them while Japan struggled to produce hundreds of inferior fighters. The technical specifications that emerged from the Corsair evaluation were later confirmed and expanded by American test programs that compared captured Japanese fighters with American equivalents. These tests reached similar conclusions, with American evaluators noting that Japanese fighters emphasized maneuverability at the expense of all other performance parameters, and that this single-minded focus on one characteristic left them vulnerable to opponents who used different tactics based on power and speed advantages. American test pilots who flew captured Zeros consistently noted that the aircraft was delightful to fly in gentle maneuvering but was fragile, underarmed, and lacked the power necessary for effective combat against modern fighters. The general American assessment was that Japanese fighter design had stagnated while American fighters continued evolving, creating performance gaps that grew wider as the war progressed. One of the most significant insights from the Corsair evaluation was how it illuminated the relationship between industrial capacity and combat effectiveness. The R2800 engine that provided the Corsair's dominant performance was itself a product of enormous industrial investment by Pratt & Whitney, which had spent years and millions of dollars developing the engine and the manufacturing processes to produce it reliably in quantity. The United States built over 125,000 R2800 engines during World War II, powering not just Corsairs but also P-47 Thunderbolts, P-61 Black Widows, and various other aircraft. This production volume required manufacturing capacity on a scale Japan could not approach. Japanese industry produced approximately 30,000 aircraft engines of all types during the entire war, less than 1/4 of the R2800 production alone. This quantitative disparity combined with qualitative inferiority created a compound disadvantage where Japanese aircraft were both individually inferior and present in far smaller numbers than American aircraft. The psychological dimension of the performance gap revealed by the Corsair evaluation extended beyond individual pilots to affect strategic thinking at the highest levels of Japanese command. Senior officers who read the evaluation reports understood that Japan was losing the aviation technology race badly and that the trend was worsening rather than improving. American aircraft were getting better with each new model, while Japanese aircraft improvements were marginal and often negated by manufacturing quality declines. As the war situation deteriorated, some officers advocated for seeking negotiated peace, while Japan still held some territorial conquests that might provide bargaining leverage. Others argued for redoubling efforts to develop revolutionary weapons that might offset American conventional superiority. The dominant view continued to be that Japan must fight to the end regardless of the odds, trusting in the courage and fighting spirit of Japanese forces to eventually achieve favorable outcomes despite material disadvantages. As we conclude this comprehensive examination of how Japanese engineers were shocked when they discovered the captured Corsair's 2,000 horsepower engine could outclimb the Zero by 3,000 feet per minute, several themes emerge with particular clarity. First, fighter aircraft design involves fundamental choices about priorities, and different design philosophies produce aircraft with very different strengths and weaknesses. The Japanese philosophy of lightweight agility produced fighters that were delightful in dogfights but vulnerable and underpowered. The American philosophy of power, protection, and firepower produced fighters that were less maneuverable, but that dominated combat through overwhelming performance advantages. Second, industrial capacity directly determines military capability in modern warfare, with superior manufacturing ability enabling production of more powerful engines, more robust structures, and more sophisticated systems that collectively create decisive advantages. Third, combat effectiveness depends not just on individual aircraft performance but on doctrine, tactics, training, and logistics, all of which must be aligned to exploit available equipment effectively. The Vought F4U Corsair earned its place in aviation history as one of the finest fighter aircraft of World War II, achieving remarkable combat success that validated its design philosophy of power and ruggedness. Japanese engineers who examined the captured Corsair in detail recognized its excellence and understood that it represented an approach to fighter design that Japan could not match with available resources and technology. The 3,000 feet per minute climb rate advantage that shocked Japanese observers was not an isolated statistic but a symbol of the comprehensive superiority that American fighters had achieved through superior engines, robust structures, heavy armament, and sophisticated systems, all integrated into coherent weapon systems that dominated aerial combat. Thank you for watching this detailed exploration of how captured American fighter technology revealed the full extent of performance disparity in Pacific air combat. If you found this comprehensive technical and historical analysis engaging and informative, please subscribe to our channel for more in-depth documentaries examining the engineering decisions in combat, realities that shaped World War II. Share this video with others who appreciate thorough military aviation history that explains both the technical details and their tactical implications. Leave your thoughts and comments below as we value our community's engagement with these complex historical narratives. Your support enables us to continue producing these detailed examinations of aviation technology, design philosophy, and the human experiences of aerial combat. Until next time, this is the story of how examination of captured technology revealed the brutal truth about design priorities and industrial capacity, and how the Corsair became the fighter that dominated Pacific skies through overwhelming power that Japanese fighters could neither match nor effectively counter, symbolized perfectly by that shocking 3,000-foot per minute climb rate advantage that represented not just superior performance, but superior engineering, superior manufacturing, and superior understanding of what modern fighter combat required.